All right, good morning. This is College Algebra, April the 2nd. Hope everybody had a good Easter weekend. And so I have a couple of announcements to make, and then we're going to get started. First of all, some stuff about Exam 2. The grades will be posted later today. I have two college algebra sections. I've gotten one of them completely done. The other one is about half done. And so those grades will get posted on your WebAssign gradebook later in the day today. If I were you, if you're watching this video, probably if you check after 4 o'clock today, you should be able to find your grade. Remember that if you want a graded copy of your exam sent back to you, please email me. And let me emphasize here to email and not to send a remind message or a WebAssign message. That would be good. That would be helpful. So email me and I'll send you back a graded copy of your exam. Also, a couple of things to note here. Don't forget that the final exam replaces the lowest exam grade. So if you have taken both exams and you've done okay on one exam and maybe not so good on another exam, remember that the final exam replaces the lowest test grade. And so, hopefully that will be beneficial to some of you. Also, don't forget that the last day to withdraw from a class and get a W in the class is April the 6th, which is this Friday. So if you have any questions at all about your grade in my class, then you should email me or send me a remind message, and we can talk about where you stand in the class and what the potential is for you by the end of the semester. Okay, so please get in touch with me. I'll be happy to discuss your grade and your situation in my class with you. Some WebAssign and homework information. Don't forget that I did not assign any WebAssign homework on section 6.1 and 6.2 and exponential functions, but I did give some homework that was in my March 28th notes. And so go back and look at the March 28th notes, and I believe it's the last 3 pages in those notes are your homework assignment on exponential functions. I want to remind you about that again, and I may include those in these notes again, but you really should be working on those homework problems and not asking you to turn that in, but it does cover the material on exponential functions that you'll be responsible for on exam 3. So kind of pay attention to that. And then WebAssign homework, you have WebAssign homework in section 6.3, the introductory section on logarithms. That's due April the 8th, and that's this Sunday, and so we'll be kind of going back to a little bit of a regular schedule as far as when WebAssign stuff has been due. And typically it's been due on a Sunday evening, though I've extended some of the dates over the last month or so. This one should not be extended, I wouldn't think, and so that's the only section you've got due on April the 8th, but you should be working on section 6.3 homework also. All right, so today we're going to cover section 6.3. We're going to look at why we need logarithms, some problems that would kind of motivate why we would need this ability to deal with logarithms. And then we're going to talk about what logarithms are, how they're inverses of exponential functions, which is why we talked about inverse functions first, is because logarithm functions and exponential functions are inverses of each other. And then we're going to look at calculating with logarithms. We're going to do some stuff with graphing calculators and how you use a graphing calculator to do some calculations. We're going to talk about what natural and common logarithms are, and then we'll finish with some basic properties of logarithms. On Wednesday, we'll look at graphing logarithms, some domains of logarithm functions, and start getting into the more important properties that we use as calculus students for logarithms. And then gradually head towards exponential and logarithm equations. That will be next week. So, all right, so let's go ahead and get started here. First thing, I have a couple of problems here. And these are compound interest problems. If you recall, we talked about compound interest last week when we looked at exponential functions. Notice that the first problem, this interest is compounded continuously, and remember that the continuous compound interest formula is A equals P times E raised to the RT power. Don't forget that E is this irrational number that's approximately equal to 2.71828 dot dot dot. It's a decimal that goes on forever. I will ask you to tell me what E is equal to on exam 3. I'll just say E is approximately equal to what? And I'd want you to be able to tell me that it's 2.718, that E has that value. Very similar to pi, which is approximately 3.14. All right, so the first problem is a continuous compound interest problem. The second problem is a finite compound interest problem, and the formula for that is A equals P times 1 plus R over N to the NT power. Right, so it's a different formula. It's a more complicated formula, a little bit more complicated formula. Also, let me mention here that there will be a compound interest problem or two on exam 3, but these formulas are not formulas that I would ask you to memorize. So on the exam 3, and if it's on the final, that it's the same for the final exam, I will supply you these formulas. These are not formulas that I would ask you to memorize. All right. Now, all right, so these two different problems as far as the way compound interest is figured. And then the other thing I want to point out is what the actual questions are in each problem. In the first problem, notice the question is how much, right, after 20 years, right? It's how much after 20 years. The second question is a different question. The second question is how long, right? And so they're asking for two different things. The unknowns are different in these two problems. The how much problem, A, is the unknown problem. The amount that the account is worth is the unknown in the problem. The how long problem, on the other hand, T is the unknown. Time is the unknown. So it's a really different question. It is a question that you would ask if you were dealing with compound interest. You know, how long before my account, if I invest such and such an amount of money in this account, how long before it is worth another amount of money, you know, $10,000, $5,000, $500, whatever, right? How long before I achieve that value? That's a valid question. It's a question that you would definitely might be interested in. All right, so let's look at the difference between these two problems and how they kind of work out. In the first problem, you've got this continuous compound interest problem. You know that the principal, the amount you're investing, is $10,000. Yay, that would be a lot of money to invest. Interest rate would be 2%, so that would be 0.02 for the interest rate. And those are really the only unknowns you've got in the in time rather, is 20 years. That's the other one. All right, so our compound interest formula would look like this. A equals 10,000 times E raised to the R, which is 0.02, times T, which is 20. All right, so that would be the calculation. And this would actually be a relatively straightforward calculator question, right, where you could do these calculations without too much of a problem. And so 0.02 times 20 would be 0.4, or 0.4. I'll put the 0 in at the beginning just to emphasize the decimal point there. So it's 10,000 times e to the 0.4 power. Remember that on your calculator, you would enter to raise e to the 0.4 power, you would hit the second key first, and then the ln key. We have not talked about what ln means yet, but you'd hit the ln key next, and then you would hit the exponent 0.4, or just 0.4, and then you would close the parentheses with a right parenthesis at the end. And then you'd hit enter at the end after that. So let's see, let me do that calculation real quick. So second ln, put in my exponent, close off the parentheses, and I get that A would be equal to 10,000 times 1.4918 power. Right, and then we multiply that by 10,000, and we get $14,918. $14,918 and about 25 cents. And that's how much money we have after 20 years. Now that may sound great, but I want you to think about the fact that, you know, it's taken you 20 years to go from $10,000 to about $15,000. So that's not really all that great after 15 years. So that's 2% is not a great interest rate. Unfortunately, bank accounts mostly are going to be less than even 1%. So, you know, just investing money in a bank account like that doesn't give you a really great interest rate at all. Okay, but that problem was no big deal. We could use a calculator. We could do the calculation. Everything was fine. Now, the second problem is the how long question, where time is the unknown now. So let's do this problem. So here, the principal is $10,000. The interest rate is still 0.02. But now this one is compounded quarterly. And since it's compounded quarterly, that means n. N is the number of times the interest is compounded per year. And so n would be 4, because that's for quarterly. If interest rate was compounded monthly, n would be 12. If it was compounded semi-annually, n would be 2. It's compounded twice a year, you know, like that. And then, in this problem, time is the unknown, but we do know A because it says that the account doubles. And when it says that the account doubles, that is telling you that A would be equal to $20,000. You know, how long before you get to the $20,000 mark is what the question is asking here, because how long before it doubles? So when you substitute everything into our formula, here's the A equals P times 1 plus R over N to the NT. You get 20,000 equals 10,000 times 1 plus interest rate would be 0.02 divided by N, which is 4. And this would be raised to the NT power. N is 4, so this would be the 4T power, like this. All right, so let's see what we've got here. So we could take 0.02 and we could divide it by 4. And that gives us 0.005. So you have 20,000 equals 10,000 times 1 plus 0.005, all raised to the 4t power. You could add those two terms together inside the parentheses. And so you get 1.005 raised to the 4t power. You could even divide both sides on this one by 10,000 to get rid of that 10,000 at the beginning. So I could divide both sides by 10,000, and I get 2 is equal to 1.005 raised to the 4t power. Now the big difference here is between this equation and the one we got on the first problem at the top of the screen is on the first problem at the top of the screen, it was just a simple calculation. And we could use our calculator to do this calculation. Here we have an equation to solve, and t, the unknown in the problem, so the unknown is in the exponent. Right? When I say the unknown, I'm talking about t in this problem. The unknown t is in the exponent, and the question is, how do we solve for a variable in the exponent? For a variable when it is in the exponent. And we have not talked about that at all this semester. In college algebra, we have never looked at an equation where the variable was in the exponent, like this one is right here. And the answer to this question is that we need logarithms to be able to solve for the unknown here. So the answer, and this is this page is really kind of just to motivate why we would need logarithms. Sometimes in application problems, sometimes in various kinds of problems, we have variables in the exponents, and the question is, how do you solve for those? And the answer is we need logarithms to do this. So we need, let's see if I can spell the word logarithm, or need, that would be good. We need logarithms. Now, it's not readily apparent, since if you have not dealt with logarithms before in a math class, you don't know what that even means at this point. So that answer only means a little bit to you probably right now, because you don't know what logarithms are. So how would a logarithm allow you to be able to solve for a variable like this is basically what we're talking about. And so that's what we want to do for the rest of class today, is talk about what are logarithms. All right, so logarithms, we're going to jump right into this. Logarithms are inverses of exponential functions. All right, now we just came out of a section where we talked about inverses. That was section 3.7 in your book. So remember a couple of key things here about inverses is that remember that inverses interchange x and y values. So remember that that inverses interchange x and y values, or they switch them around. So what we're going to do is we're going to start off with an exponential function, and we're going to look at its inverse. So remember that an exponential function is a function that typically looks like this: f of x equals b raised to the x power. That's a simple form for an exponential function. And what we want to do is we want to find f inverse. Remember, that's red. You read that f inverse right here. When I use that notation of a -1 on the function name, remember, that's not an exponent of -1. It's not an exponent. It's just notation. All it means is you're talking about the inverse of the function f. And so remember how we do this. We first, in place of f of x, we write y. And then what we do is we switch x and y. So if I switch x and y, I get x equals b raised to the y power. Right? So that's where I did right there in that step, is I switched x and y. All right, and then the next step after you've switched x and y is you solve for y. In other words, you want y equals here. And notice the y is in the exponent right here. And to solve for y, what we do is we introduce this new notation right here. And this new notation is that y is equal to the logarithm base b of x. That's called logarithm base b of x. And so that's how you read that. So you read this as log, and it's usually abbreviated log, not logarithm, but log base b of x. Notice that b is written down below the logarithm line, so it's actually what we call a subscript. And that is not a calculation, that's just the base on the logarithm right there. All right, this form, those last two statements right there, if we write those down again, you have x equals b to the y, and you have y equals logarithm base b of x. Those are equivalent statements. These are the same statement, just written in different form. So those are equivalent. So when I say equivalent, they mean the same thing. It means that you can interchangeably write one of them or the other one. The first one is sometimes called the exponential form of the expression. And the second one is sometimes called the logarithm form, or just the log form. and they're interchangeable, like I said. But they mean the same thing. So now, if you look at that, if you look at them right next to each other like this, y equals logarithm base b of x, that it's equivalent to b raised to the y equals x, that those mean the same thing. Let me make a better double-ended arrow there. That those mean the same thing. Then that logarithm base b of x, notice what the y is. The y, if you look at the exponential form, the y is the exponent right here. And what is it? Y is the exponent that you raise b to get x. So one way to look at this in words is that logarithm base b of x equals y, or let's not even say equals y. Let's just write it like this. This represents the power you would raise b to get x. That's what that means. And all I'm doing is taking that directly from the fact that the exponential form and the logarithm form are equivalent right here. That they mean the same thing. And so I'm kind of piecing those two things together to say in words that what has to be true is that logarithm base b of x represents a power. It's equal to a power. Because if you look at it, notice I've got logarithm base b of x is equal to y. But if you look at the exponential form, y is the exponent. So a logarithm is equal to an exponent. And the question is, what exponent is it equal to? It's equal to the exponent. You would raise the base on the logarithm to get the number x. All right, so now I'm going to flip the screen here, but I'm going to write down a few things at the top. And by the way, there's another thing that we're kind of glossing over right here that we'll talk more about in a little bit. But, you know, remember what started this was this exponential function. And so we got this logarithm function by finding its inverse. And so the inverse, one thing we did do here is we showed that the inverse of the exponential function b to the x was the logarithm function log base b of x. Now this is... I'm going to talk about this more at the end of class again today, but this is also another relationship that comes from this page that we need to talk about, is that exponential functions and logarithm functions are inverses of each other. But I'm going to wait until the end of class to go back and look at that relationship. What we want to do is focus on this relationship right here at the very end of the page, the relationship between the exponential form and the logarithm form of a logarithm statement, right? And what that actually implies as far as calculating with logarithms. So that's the form we're going to focus on right now, or that's the statement we're going to focus on right now. And then later in lecture today, we'll go back and look at how logarithms and exponential functions are inverses of each other. All right, so... go back one more time. The very bottom statement here. Right? Let me highlight this in a different color. Logarithm base b of x represents a power that you would raise the base b to get x. So, logarithm base 2 of 8. Then this would be equal to an exponent, right? This is going to be equal to an exponent. And what exponent it's going to be equal to? It's going to be equal to the power you would raise the base on the logarithm, which in this case is 2. So the power you would raise 2 to get 8. It's the power you would raise 2 to get 8. So you're asking yourself, 2 to what power is equal to 8, right? That's the question here. And notice I wrote one down that you should be able to figure out, right? That this is going to be equal to 3, right? 2 to the third power is equal to 8. And so logarithm base 2 of 8 has the value 3. That's what it's equal to, right? We've done our first calculation with logarithms. All right, so logarithm base 5 of 25. So what we're going to do is go through and practice this to start off with. Logarithm base 5 of 25. In words, this would be the power, right? All logarithms, remember, are equal to exponents. What you're trying to do is figure out what the exponent is. The power you would raise 5 to get 25, right? So this is equal to some power right here. And that power, what is it? It's the power that you would raise 5 to get 25. And the power you'd raise 5 to get 25 is 2, right? I'm writing statements down right now where we can figure these out without using a calculator or anything like that. So what do we get here? That logarithm base 5 of 25 is equal to 2, right? That's the value of that logarithm.
How do you get 2?
What power? Okay, so look at the words right there again, Anne-Marie. That logarithm base 5 of 25 represents a power.
So we're basically squaring it?
Yep. That you're saying, what power do I raise 5 so that I get 25 is the answer? In this case, it's 2, right? It just happened to be. So like, if we continued, let's say we still have logarithm base 5. It's still logarithm base 5, but the number that we're going to taking the logarithm of is different. Let's say it's the equal to 125. Okay, so it's logarithm base 5 of 125. So this would be 5 to what power is equal to 125? That's the question that you're asking yourself in order to be able to answer this, in order to be able to calculate this. So Anne-Marie, what power do you... Whoa. All right, so getting back to the lecture here. So you have logarithm base 5 of 125. Then this is asking you a question. It's saying, hey, this is equal to an exponent. What exponent is it equal to? It's equal to the exponent that you would raise 5 to get 125. And just before my recording went kind of crazy there, Anne-Marie had said that 5 to the third power was equal to 125. So that's the value of logarithm base 5 of 125. It's equal to 3. It's equal to an exponent. What exponent is it equal to? It's equal to the exponent you would raise 5 to get 125. All right, logarithms are always equal to exponents. And so the question is, what exponent is it equal to, right? So you have to look at the base that you're talking about in the problem and, kind of go from there. So let's look at, and so that's what I'm doing right now is just looking at a bunch of these so we can kind of get used to that. So logarithm base 3 of 3. What is this equal to? It's equal to an exponent, right? And I'm just putting a box where the exponent is right now. And what exponent is it equal to? It's equal to the exponent that you would raise 3 to equal 3, right? 3 to what power is equal to 3? So you guys who are listening to me live today, 3 to what power is equal to 3? Yeah, it's 1. That's right. And so logarithm base 3 of 3 is equal to 1. Right, because that is the exponent you would raise the base to get the number you're taking the log of there. Right, it's always equal to an exponent. Logarithm base 10 of 10,000. Now don't freak out here. You can do this. 10, you're saying here, okay, I'm raising 10 to what power? When I put a big box there, I don't really know why. 10 to what power is equal to 10,000? Anybody know?
Is it 3? Yeah.
No, when you take 10 and raise it to a power, you always get the same number of zeros as the exponent, right? So, right? 10 to the, yeah, that's right. It's 10 to the first power is 10. 10 to the second power is 100. 10 to the third power is 1,000. 10 to the fourth power is 10,000, right? The exponent's always equal to the number of zeros. So this is equal to 4. Logarithm base 10 of 10,000 is equal to 4. Let's see. Logarithm base 6 of 36. What's that going to be equal to?
2?
It's going to be equal to 2. That's right. Because, very good, because 6 to what power is equal to 36? That's the question that you're asking yourself off to the side there. And that's equal to 2. So this is equal to 2 right here. Now, the calculation we're interested in is the left side, right? And what am I doing in each case here is I'm writing what's called the log form down. And adjacent to it, I'm writing the corresponding exponential form. What I've been doing is writing the corresponding exponential form. And the exponential form just usually gives you an easier opportunity to be able to figure out what the exponent is for a problem like the ones that I've been writing down. All right, logarithm base, let's do something like this. Logarithm base 4 of 1/4. Now this one might be a slightly trickier, but we can still do this. So this is 4 to what power is equal to 1/4? Right. So what has to be true about the exponent in order to turn it into a fraction, in order to flip it upside down? What do you have to have on the exponent?
You have to make it the square root.
No, not a square root. What flips a fraction? What kind of an exponent?
Multiplication?
No, what kind of a fraction flips an exponent? What kind of a, I don't know if I said that right. What kind of an exponent? I may have actually answered the question inadvertently. What kind of an exponent flips a base like that? If you remember, let's just do this off to the side over here. Remember that
Is it the inverse?
3 to the negative 1, remember, is equal to 1/3. Remember that a negative exponent flips the fraction. It's got to be a negative exponent. 3 to the negative 2 is 1/3 squared, right? Remember that a negative exponent flips the base like that. Right, that's what I was looking for. So 4 to what power is equal to 1/4? -1. Right, because 4 to the negative 1, it would flip it and you get 1/4 like that. And so logarithm base 4 of 1/4 is equal to -1. That's its value. Don't forget, a negative exponent flips a fraction. Don't forget, a fraction is an exponent is a root. And so maybe let's look at some exponent rules here just to remind you. Exponent rules reminder here. Remember that when you have something raised to a negative exponent, like x to the negative n, that's 1/x to the n. Right, so 5 to the negative 2 would be 1/5 squared. X to the negative 6 would be 1/x to the 6th. Right, those are examples of that rule. And then if you have x to the a over b, that if you have a fraction as an exponent, remember that the numerator is the power and the denominator is the root. So for example, if you have 27 to the 2/3 power, that is the cube root of 27 to the 2nd power, or 3 to the 2nd power, or 9, right? Because the cube root of 27 is 3. X to the 4/5 power would be the 5th root of x to the 4th power. Right? Remember that the numerator is the power and the denominator is the root. So that's probably something worthwhile to write down because we're going to use both of those properties frequently the rest of this lecture. So that's just kind of a reminder of some exponent rules right there. All right, so let's get back to our logarithm discussion here. So logarithm base 8 of 1/64, since we're talking about negative exponents. Logarithm base 8 of 1/64. Okay, so this is saying 8 to what power is equal to 1/64, right? So what am I going to have to do? I'm going to have to flip it, right? So because I'm going to have to flip it, the exponent's going to have to be
Negative 2?
Negative, that's right. And somebody said negative 2, that's exactly right. It's going to have to be negative, and it's going to have to be negative 2. And so that's the value of this logarithm. It's logarithm base 8 of 1 over 64 is negative 2. Logarithm base 2/3 of, let's say, 9/4. Now it's getting a little bit tricky, but I'm going to do one more with a negative exponent. I don't want to get too bogged down in the negative exponent stuff, but I do want to talk about that a little bit here. So logarithm base 2/3 of 9/4. So this would be 2/3 to what power is equal to 9/4. So what's going to happen? I'm going to have to flip it, right? Because that's the only way I'm going to get a 9 in the top and the 4 in the bottom. So the exponent's going to have to be negative. And what am I doing? I'm squaring the 3 and I'm squaring the 2. So it's going to be a negative 2 also. So this is negative 2 here as well. All right. So a logarithm can be equal to a negative number. Certainly. There's no question about that. Let's see. Logarithm base, since we're talking about those rules at the top, logarithm base 4 of 2. Now, at first, that might look kind of tricky because you've got 4 to what power is equal to 2? That's the question, right? 4, you're raising 4 to what power to get 2? But what are you doing here? You're taking the square root of 4, aren't you? Jennifer, yes, Jennifer answered, and she said 1/2. That's exactly right, Jennifer. She chatted me the answer there, which is exactly right, because you've got, what are you saying? You're saying the square root of 4 is equal to 2. And how are you taking a square root here? You have to use an exponent of 1/2, right? And so this exponent has to be 1/2 right here, right? And Jennifer said, could you put a decimal of 0.5? And absolutely you could do that. There's no question that you could do that. That would be okay to do. Hold on real quick here. Okay. Let's see. So if we had, back up here. So if we had logarithm base, let's say 64 of 4, logarithm base 64 of 4, this would be saying 64 to what power is equal to 4. But what are we talking about here? To get to 4 from 64, when you're talking about roots and exponents, this is a cube root. The cube root of 64 is 4. And so what exponent do you use for a cube root? 1/3. Right? So this is the 1/3 power right here. And Jennifer answered it also on chat up there. Very good, Jennifer. And that it's going to be 1/3. The 64 to the 1/3 power has got to be equal to 4. Right? It's because it's got to be a cube root. All right, let's see. How about something like this? Logarithm base 10 of 1. See if we can get this one. So what's this going to be? This is going to be, what power do you raise 10 to get 1 is the answer. What power do you raise 10? And what did you say, Charlotte?
0.
Very good. And Jennifer also said 0 on chat. That's both of you, very good. 10 to the 0 power is equal to 1. This has got to be equal to 0. So a logarithm can definitely be equal to 0. Because when you have the log of whatever the base is, what I want you to look at here is, it's not a 6 there, it's a b. Logarithm base b of 1 in general is always going to be equal to 0 because b to the 0 power is equal to 1. This is actually kind of a property for logarithms, that logarithm base b of 1, the log of 1 is always 0, no matter what the base is. That you don't have, if you don't even have to worry about necessarily doing an exponent calculation there. So logarithm base 6 of 1 is 0. Logarithm base 10 of 1 is 0. Logarithm base 18 of 1 is 0. It doesn't matter what the base is, the log of 1 is always 0. And then what about, let's say we have log base 7 of 7. What's logarithm base 7 of 7 going to be equal to? I heard a couple of you maybe whisper it, but that's right. It's going to be 1. 7 to the first power is equal to 7, right? It's the power you raise 7 to get 7. And so that's going to be equal to 1 right there. So that's actually a property also, because notice the base on the logarithm and the number you're taking the log of were the same. So that property is logarithm base b of b. When those numbers are the same like that, that value is always 1. That's also a nice little property for logarithms to know, that logarithm base b of b is always equal to 1. So logarithm base 5 of 5 is equal to 1. Logarithm base 3 of 3 is equal to 1. Logarithm base 1/3 of 1/3 is equal to 1. Right, and so on and so forth. Logarithm base, you could use this number, this crazy number e that we've talked about. Logarithm base e of e is equal to 1. Those are all the same property. Right, that logarithm base b of b is always equal to 1. All right, this one is sort of a trick question. Logarithm base 2 of -4. In some ways, this is a trick question here. So don't worry about answering it at this point. But what are we saying here? We're saying 2 to what power is equal to -4? Right, that's the question. 2 to what power is equal to -4? But the problem here is that when you take 2 and raise it to a power, it doesn't matter what power you raise it to, whether it's a negative power, right? Like, think about it. Remember what a negative power does is a negative power turns it into a fraction. It doesn't make it negative. Whoops. Right, just makes this 1/8. 2 to the -2 is equal to 1/4. 2 to the -1 is equal to 1/2. What I want you to see is that no matter what power you raise 2 to, you never get a negative answer. And so this can't be done. And so generally speaking, not really a property, but something that we want to definitely observe here, this is important for us, is that logarithm base b of x, that x must be positive. X can't even be 0, right? It's got to be positive, right? So x has got to be greater than 0, right? That's important. So let's go ahead and just write it this way: logarithm base b of x, x must be greater than 0, and the base has to be greater than 0 also, by the way. Not necessarily a property, but definitely something that we need to know about logarithms, is that you can't take the log of a negative number, right? You can only take logs of positive numbers. So that's important also. All right. Now, there are some logarithm bases that are bases that are more important than others. And the two most important logarithm bases are logarithm base 10 of x. Logarithm base 10 is a common logarithm to use, and that's actually its name. It's called the common logarithm, or just the common log. And the abbreviation for log base 10 of x is just log x. When you see a logarithm written down without a base, it is understood to be base 10. Right? So these are called common logarithms, and it's base 10 logarithms. So, for example, if I write log of 100, log of 100 is simply the log base 10 of 100. Right, it's an abbreviation for log base 10 of 100. And logarithm base 10 of 100 is equal to 2. It's the power you raise 10 to get 100, and that would be equal to 2. So log of 100 is equal to 2. Log of 1,000 is an abbreviation for log base 10 of 1,000. And that's the power you raise 10 to get 1,000, and that would be equal to 3. Like that. So when you see a logarithm written down with no base written down like that, then it's understood to be a common logarithm or a base 10 logarithm. There is another base that is important when you're talking about logarithms, and that's base e logarithms. So you have logarithm base e of x. This is called the natural logarithm, or just the natural log, and the abbreviation for the natural log is lnx. Right, it's called a natural logarithm, and the abbreviation is lnx. So you frequently don't, most of the time, don't write it as log base e. You usually write it as ln. So ln of, let's say, just e, ln of e, is an abbreviation for logarithm base e of e. And logarithm base e of e, we know is 1. The natural log of e squared would be equal to, an abbreviation would be logarithm base e of e squared. And so I want you to think about this one for a second. This makes sense. This is, what power do you raise e to get e squared? Well, that would have to be 2. Right? So notice that the natural log of e squared is just equal to 2. Because that's the power you raise e to get e squared. Natural log of the square root of e. A little bit tricky, but we can do this. This is an abbreviation for logarithm base e of the square root of e. Well, square root of e. And that is, let's see, that's the logarithm base e of e to the 1/2 power, because that's what square root means. As an exponent is 1/2 power. And so what's this one? As an exponent, this is e raised to what power is equal to e to the 1/2? And that would be 1/2. Right? So the natural log of the square root of e is just equal to 1/2. The important thing is when you see ln of e, ln of something, you're talking about a logarithm base e. All right, on your calculator. Your calculator speaks in 2 bases, only. It speaks in base 10, and it speaks in base e. And on your calculator, you've got a log key. That's what's got written on it, log. And you've also got an ln key, ln like that. And so that is how you would use those keys to evaluate logarithms if you're going to do a calculator problem. So far, every problem I've written down is a problem we didn't need to use a calculator for. But look at this one right here. If let's say we had the log of, let's say, 250. Log of 250. Now remember what this is an abbreviation for. This is an abbreviation for logarithm base 10 of 250. And as an exponent, this is asking 10 to what power is equal to 250. All right, 10 to what power equals 250. But what's the problem here? 10 to the first is 10, too small. 10 to the second is 100, too small. 10 to the third is 1,000. It's too big, right? So 1 is too small. 2 is too small. But 3 is too big. So what's true here? That there's got to be some number between 2 and 3 where you take 10 and you raise it to that power and you get 250. This is a calculator question. Right? So on your calculator, what do? You just enter log of 250 on your calculator. So you literally hit the log key first, and then you hit 250, and then close the parentheses. And when I do that on my calculator, I get 2.3979 approximately. 2.3979. That's just an abbreviation, or an approximation, I should say, to 4 decimal places, about 2.3979 power. You could actually check this on your calculator if you wanted to. So check on your calculator. You could take 10 and you could raise it to the 2.3979 power. Remember that caret symbol is raising to a power. And when you do that, I get about 249.97 power. About 249.97 power. Close to 250. It wouldn't be exactly 250 because, you know, remember I've rounded the decimal. But that would tell you that you're quite likely correct right here for log of 250. All right. So another calculator question. Let's say we had the natural log of 100. ln of 100. So the natural log of 100 would be an abbreviation for log base e of 100. Right? So that's just an abbreviation for log base e of 100. And this is the power you would raise e to get 100. It's not something you would know, right? That's not an exact value at all. You would use your calculator to do this problem. So on your calculator, you would enter, you know, the natural log key. You'd hit the natural log key first, and then hit 100, and then you hit the right parenthesis to close off the parentheses. And so when I do that, I hit ln 100, close the parentheses there. I get like 4.6052, rounding it to 4 decimal places. So I get the natural log of 100 is approximately 4.6052. I've rounded it to 4 decimal places. So rounded to 4 decimal places. Right, and so what does that number represent? It's the power you would raise e to get 100. So to check this on your calculator, you could do e raised to the 4.6052 power. And remember, to do e, to enter e to a power in your calculator, you have to hit the second key first, and then the ln key. You hit second ln, you're taking e and raising it to a power. So when I do second ln of 4.6052, I get 100.002 approximately. 100.002. And that's, approximately 100. It's a little bit too big. When I rounded the decimal, I rounded it up. So it makes sense that you should get something that's a little bit too big right there. All right, so a little bit about natural logarithms and common logarithms, base 10 logarithms and base e logarithms. Those are definitely logarithms that you need to have a good understanding of what they're an abbreviation for. All right, so now let's kind of talk more specifically about going back and forth between exponential form and logarithm form. We've really been doing that with these calculations, but now I'm going to kind of shift the emphasis a little bit. So let's say we have logarithm base 3 of x is equal to 5. Right? Logarithm base 3 of x is equal to 5. So that would be the logarithm form of an expression. And so the exponential form, so if you're going to write this in exponential form, right, this is 3. The base, notice the base on the logarithm and the base on the exponential expression are the same. 3 to the 5th power is equal to x. That would be the exponential form. Right, this is the log form right here, and this is the corresponding exponential form right here. Now, notice you could actually figure out what x was here because you just take 3 and raise it to the 5th power. logarithm base 2 of x plus 5 is equal to w. All right, so that would be a log form for an expression right there. And so the corresponding exponential form, remember the base on the logarithm and the base on the exponential form are the same. So this would be 2. Remember that the logarithm is equal to the exponent. Logarithm is always equal to an exponent. So the w has to be the exponent. 2 to the w equals x plus 5. Right? That's the exponential form for that corresponding logarithm form. Logarithm base 5 of uh, 385 is equal to z. Logarithm base 5 of 385 is equal to z. So that would be the log form right there. So the corresponding exponential form would be 5. The bases are the same, raised to the z. Remember, the logarithm is equal to the exponent. So z has to be the exponent, is equal to 385. That would be the exponential form for that logarithm form. All right, let's look at our important logarithms here. So let's say we have log of 2x plus 4 is equal to 3. Log of 2x plus 4 is equal to 3. So remember, there's no base written right here. So this is understood to be logarithm base 10 of 2x plus 4 equals 3. And so this is our logarithm form right here. And so the corresponding exponential form would be 10, because the base on the logarithm is 10. The base on the exponential expression has to be 10. The logarithm is equal to the exponent. So 3 has got to be the exponent, is equal to 2x plus 4. All right, this is be the exponential form right here. 10 to the third power equals 2x plus 4. Notice you could actually solve that equation for x, which we'll be doing later. Natural log of z plus 3, excuse me, is equal to x plus 1. Natural log of z plus 3 is equal to x plus 1. So this logarithm is an abbreviation for logarithm base e. And it says logarithm base e of z plus 3 is equal to x plus 1. So this is our logarithm form right here. And so the corresponding exponential form, the bases are the same. The base on the logarithm is e, so the base on the exponential expression has to be e. The logarithm is equal to an exponent, so that means x plus 1 has to be the exponent. And then that would be equal to z plus 3. And so that would be the exponential form right there for that given logarithm form. All right, now let's go back the other direction. Let's start with exponential forms and let's write logarithm forms. So let's say we have 8 to the x plus 3 is equal to, let's say, 64. All right, so this is an exponential form right here, and so we want to write the corresponding logarithm form. So what do we know? That the base on the exponential form and the base on the logarithm form are always the same. So the base on the exponential form is 8, so the base on the logarithm is 8. So the logarithm base 8, remember to write it as a subscript. It's not written right next to the logarithm, it's written below the logarithm there. So the logarithm base 8 of something equals, and remember, a logarithm must always be equal to an exponent. So the exponent in this problem is x plus 3. So this is logarithm is equal to x plus 3. So what is this? This is logarithm base 8 of 64 is equal to x plus 3. And so this is the corresponding logarithm form right here. So now we're converting from exponential form to logarithm form. All right, let's say we have a to the 35th power is equal to 2x minus 1. All right, that's an exponential form right there. Kind of a crazy exponential form, but it is an exponential form. So what do we have here? That the base on the exponential form and the base on the logarithm have got to be equal to each other. So the base on the exponential form is a in this statement. And so that would be the base on the logarithm. It would be logarithm base a. And remember that a logarithm is equal to the exponent. So this is logarithm base a of something has got to be equal to 35. Because 35 is the exponent in this problem. Right? And what is it? It's logarithm base a of 2x minus 1. Right? This would be the corresponding logarithm form. All right, if we have 10 to the 3x minus 1 is equal to 1,000. 10 to the 3x minus 1 equals 1,000. So this is a base, notice this is a base 10 exponential expression. So the logarithm would be logarithm base 10. Logarithm has got to be equal to the exponent, so it's got to be equal to 3x minus 1, and this would be the log of 1,000. Log base 10 of 1,000. Now that's not how you'd write it because this is logarithm base 10. So you typically see this as simply log of 1,000 equals 3x minus 1. You typically don't write the base when it's a base 10 logarithm like that. So that would be the abbreviation. So this is our exponential form right here. This is our corresponding logarithm form right here. All right, if we have e to the 3x is equal to 5/4. E to the 3x equals 5/4. So this would be logarithm base e, right? Because the base on the exponential expression and the base on the logarithm have to be equal. The logarithm is always equal to the exponent, so this has got to be equal to 3x. So this would be logarithm base e of 5/4 is equal to 3x. And again, that is not how you'd leave it. You wouldn't write it that way. Logarithm base e, you'd always write as ln. So this would be ln of 5/4 equals 3x. I'd always want you to use the abbreviation. That's the abbreviation your calculator uses. That's the abbreviation you're going to see in the textbook. Those are the abbreviations I'd want you to use for common logs. Right, this is a common log right here, and this is a natural log right here. All right, so let's write that down, kind of the general statement again one more time, that you have logarithm base b of x is equal to y is the logarithm form. And that would be equivalent to b to the y is equal to x, right? This is the log form right here, and this is the exponential form right here. Also, don't forget that logarithm base b of x in words means that this is equal to the power you raise b to get x, right? And so that's useful to think of it that way when you're thinking of trying to do a calculation with a logarithm, especially if it's something that you can actually calculate kind of in your head if you know what the power is. Excuse me. We know that logarithm base b of b is equal to 1, no matter what the base is. And we know that logarithm base b of 1 is equal to 0. We know that logarithm log of x is just an abbreviation for log base 10 of x. And we know that ln of x is an abbreviation for log base e of x. All right, and then the last thing I wanted to kind of talk about here, and what I'm doing, if you notice here, is I'm kind of summarizing all the things we've done with logarithms so far. we know that log base b of, if you're looking at log base b of x, that x must be positive. In other words, you cannot take the log of a negative or 0, right? That you can only take logs of positive numbers. All right, and then the final thing, and we talked about this at the very beginning when we were talking about logarithms, that we have is that if f of x is equal to an exponential function b to the x, then the inverse for that function is logarithm base b of x. The exponential and logarithm functions are inverses of each other. So I do want to write a few examples down with that and some properties that we get from that, and then that will finish it. So we've got about 5 minutes left here. So if we have that f of x is 2 to the x, if that's an exponential function that we get, then the inverse for that exponential function is logarithm base 2 of x, right? That the log base 2 of x and 2 to the x are inverses of each other. We have f of x is 5 to the x, then its inverse is logarithm base 5 of x. Right? That function 5 to the x and log base 5 of x are inverses of each other. We have f of x equals e to the x. Then its inverse, that's e to the x right there, it would be the log base e of x, and remember that's ln of x. So the natural log of x and e to the x are inverses of each other. Very, very important that we're going to talk about later. And 10 to the x, its inverse would be log base 10, which is just log x. Right? Log x and 10 to the x are inverses of each other. By the way, on your calculator is actually telling you that both of those things are true. That's actually on your calculator keyboard. You never have to worry about remembering this because it's on your keyboard. Because if you look at the ln key on your calculator, and it's not ln x, by the way, it's just ln. If you look at the ln key on your calculator, right above it is e to the x. It's actually telling you that ln and e to the x are inverses of each other. And on the log key, right above log, is 10 to the x. It's telling you that log and 10 to the x are inverses of each other. Log x and 10 to the x are inverses of each other. So in your calculator, that actually is written out like that. Let's see, if we have f of x equals log base 2/5 of x, then its inverse would be an exponential function, right? This is a logarithm function, so its inverse would be the exponential function 2/5 to the x. And then finally, the fact that these are inverses, exponential and logarithm functions, means that you have inverse cancellation. And remember what inverse cancellation meant when we did inverses is if you took two functions that were inverses of each other and composed them, you just always ended up with x as the answer. Right? That when you compose two inverses, that they cancel each other out. So what happens is, if you have 3 to the log base 3 of x, notice that the exponential function here is 3, because that's the base there. And then the base on the logarithm is also 3. Those are inverses of each other. And so they cancel each other out, and you end up with x as the answer. 10 to the log x. Well, the base on that logarithm is 10, and so sure enough, those are inverses. That's an exponential function of 10 and a logarithm that's base 10. Those cancel each other out. You're left with x. And that is another property that we can, I had this summary of properties here on this page. But this is the property. Let's see. So the property I was using was that b raised to the log base b of x is equal to x. That's called inverse cancellation there. That's just because they're inverses. And it actually works the other direction also, that logarithm base b of x, I'm sorry, of b raised to the x power, had that written wrong, b raised to the x power, once again, the base on the logarithm and the base on the exponential are the same. That's x also. This is called inverse cancellation, and this is because they're inverses of each other that this is always true. So those are two useful properties to have also. So that was some examples at the very bottom of the page there. And you could also have like log base 5 of 5 to the x, right? Notice if the base on the logarithm and the base on the exponential expression are the same, then you're getting inverse cancellation. So you get x there. And if you have natural log of e to the z power, what's the base on that logarithm? Well, that's an ln, so its base is e. And so sure enough, the base on the logarithm and the base on the exponential expression are the same. And so you get z. They cancel each other out, and you get z there. So those are some examples of inverse cancellation there at the bottom. Not incredibly important properties, but they're useful properties to know when you're talking about calculating with logarithms. Now I know coming out of this first lecture on logarithms, you can get a little bit nervous about what you're doing. But first, the last thing to write down here is that logarithms are exponents, right? They're just another way of writing exponents. So when you talk about a logarithm here, a log, no matter what the base is, no matter what this expression is, what's it always equal to? It's equal to an exponent. So that's the last thing to kind of keep in mind. And what does that exponent have the property of? That when you take b and raise it to that exponent power, whatever it is, you get whatever is inside the parentheses. Right? So logarithms are exponents is an important kind of phrase to remember when coming out of this first lecture. That's probably the single most important property. Now, it'll start coming together a little bit better the further we get into this. So on Wednesday's lecture, as we get it further into logarithms, some of these pieces will start fitting together better and better as we go along. So be patient with it. Go through, there's lots of practice problems on WebAssign on section 6.3's homework. So that's an important homework assignment to look at for review on this. Lots and lots of examples of the kinds of things that we've been talking about. It's a lengthy exercise because there's 30 questions on it, but they're all short answer. And lots of answers like what we've been talking about right here. All right? So if you have any questions, ladies, Anne-Marie, Charlotte, are you guys okay? Well, I don't know if you're okay or not, but do you have any questions?
No questions.
Okay, it can be intimidating at the beginning, so just be patient with it, okay?